Hi everybody, I'm Max. Today I'm going to talk about my ELS 2020 paper titled Later Binding, Just-in-Time Compilation of a Younger Dynamic Programming Language. And yeah, nice to meet you all on this year's virtual ELS, and let's dive right in. To give a little bit of context, previously I've worked on a project called Snap. Snap is a high-performance toolkit for packet processing. The intended audience are telcos and network operators in general. In Snap, we process millions of packets per second per core using a high-level dynamic language. And this is possible thanks to a compiler, a just-in-time compiler for Lua, the dynamic language that we're using for writing Snap, that is really, really fast and generates really, really good code. So the paper that I've submitted goes in much more detail than this talk will go over how LuaJIT and its tracing just-in-time compiler work, and its differences compared to traditional ahead-of-time compilers such as used commonly in Lisp implementations, as well as its advantages and some downsides, or as I would say, remaining bugs. So let's look at how the LuaJIT tracing just-in-time compiler works. At the heart of LuaJIT, there's a good old-fashioned interpreter. This interpreter will interpret the bytecodes that make up the Lua program. When the interpreter hits a branch, however, it does some JIT-specific logic. Every branch has maintained a hot counter, so-called hot counter, I would say, which tracks how often the branch is executed. If a branch is not yet considered hot, then the hot count will be incremented and the interpreter will continue interpretation of the program. However, when a branch becomes hot, then the interpreter, the LuaJIT VM, will start recording a trace and continue interpreting the program while recording the next instructions to be executed. And at certain conditions, this recording stops and the resulting instruction trace will then be used to compile a machine code sequence that in future occasions of this branch will be executed instead of the code that would usually be interpreted. So this is quite different compared to the traditional ahead-of-time compiler, which looks at the source code before it is run and tries to find a good translation of that source code into machine code, whereas the JIT compiler looks at the program while it's running and generates traces and compiles those from the actually executed code. And this has some implications because at runtime you have, especially in a dynamic language like Lua or Lisp, a lot of type information available, and it can use that to optimize the code. So let's look at a simple program here written in Common Lisp and compiled by a Common Lisp implementation, in this case CCL, that is Closure Common Lisp. So here we have a little function that consists of a loop that sums the integers or the numbers actually from 1 to x. And if we look at the disassembly of that program, we can get some idea of how the CCL ahead-of-time compiler works. Notably, we can see that the loop body starts here. And what we see, and what is very characteristic of Lisp code compiled ahead of time, is that the code will, at least without annotations, static annotations that is, have things like type checks performed at runtime, in this case to see if the looping index variable is a small integer or not. If it's not, then it will branch to a generic arithmetic function for other number types. Otherwise, it will do the optimized or the fast pass small integer comparison and continue on to do its work. Likewise, the program doesn't know ahead of time if the loop index will overflow. So even on the fast pass, when it has checked at runtime that the loop index variable is a small integer, it will have to handle overflow and subsequent eventual promotion to a big int. And as you can see, this loop is really full of these branches where at runtime certain types are checked and handled in exceedingly generic routines. All right, so what does this tell us? Even though we have a lot of runtime information available, type information available at runtime, this information cannot be always used at compile time to generate good code. In the emitted code, we see a lot of specialization and despecialization of the runtime values, as well as runtime overflow checks. And the runtime information is actually not used for optimization. If we now look at a similar program written in Lua and compiled by LuaJIT, we can see a couple of interesting things happening. So if you look in the top right here, this is how you run a Lua program with LuaJIT. And this flag here says dump the generated code and the immediate representation and the bytecodes that you're compiling while you're executing it. Can run this for a bit. So now it ran, it printed the right answer, as you can see right here. And here we can see the machine code for the one and only trace that it compiled while running this program. And below here you have the loop body, which I've also pasted in here for simplicity. All right, so looking at this, a couple of things pop out. First of all, I've explained to you how the compilation model differs. This is not compiled ahead of time, but only while it's running. If, for example, I changed the iterations here to 1, then what you would see is just the answer and nothing being compiled, because the trace compiler didn't kick in, because no branch ever got hot. So that's one interesting thing. The second interesting thing is that the loop body is really much tighter than in the common Lisp code. And most notably, you can see here that LuaJIT used runtime information to infer that in this particular case, the index variable of the loop can never overflow and will always be a small integer, and emits code accordingly. Also, something that at this point should be clear is that compared to an ahead of time compiler, we operate with a really different unit of compilation here. So in the common Lisp example, the unit of compilation was the function. In this example, the unit of compilation is really this loop here. And even more so, an invocation of this loop where x has a specific value, or at least a specific type of value. So let's look at some other examples here. In this example, I've used some object-oriented abstractions to essentially construct the same code. It does the same thing. The only difference is that here we have a new class or prototype, however you want to call it, ag. It has a constructor which initializes some instance state, and it has a method where it accumulates n to the instance state. We can instantiate the accumulator. We can call its method in a loop and print the result, which will indeed print the same result, I promise you. And interestingly, if you look at the code that's emitted to be run, it's essentially the same. The only difference here being that we have a move to memory instead of to register. So how can that be? Again, LuaJIT was able to use runtime type information to abstract away and hoist all the safety features and the object-oriented patterns and abstractions out of the loop and generate really, really tight inner code for the fast pass. So as we can see here, all these high-level abstractions are completely melted away. So to drive this point home even further, we're going to look at another example. So in this case, I've used some functional abstractions. We have here a higher order function that creates a closure with a closed over accumulator variable and some gratuitous polymorphism where depending on the type of X, we do certain different things. If it's a number, we accumulate it to A. If it's a string, we concatenate it to A. And if we have no parameter at all, if X is nil, then we return A. We create our closure, our accumulator closure, we run it in a loop. And again, we get the same tight inner loop body as before, without even any of the branches in that closure. So what we see here is that because of how the recording happens, and let's look at this, right? So if you remember, we record only the instructions that we actually execute at runtime into a trace and then compile that trace. So what you see here is the machine code generated for the bytecode trace that was actually run in this example, stripping away all the abstractions, leading to this very tight code. And interestingly here, something that you should know is that this is a form of speculative compilation, because what the compiler essentially did is say, okay, I'm seeing that right now, while I'm executing this loop many times, what I'm actually doing is executing this code path. So speculatively, I'm going to compile a loop for this code path so I can run this quickly. So in the previous example, we've seen how LuaJIT can even eliminate branches within loops if it can infer so from runtime values or the runtime types of values. And in this example, I want to go a little bit into how LuaJIT behaves if it can't hoist a branch outside of the loop body. So here we have a loop that iterates from 1 to 100 and will accumulate only the odd indices within the loop. And below here we have the compiled traces. LuaJIT will compile this to two traces. The first trace here starts with the loop prologue, where it does all the dynamic runtime type checking and setup that you would expect from a dynamic language, and then enters this very tight loop body, which is specialized for the odd indices. So here it checks if the index is odd. And if it isn't, it will bail from that trace. And this is what in LuaJIT terminology is called a guard. So, right, we have the version for the odd branch. So far so good. If all our indices were odd, this would indeed be very, very fast and tight code, just as before. However, our branch in this case is unbiased. So what will happen in every other iteration of this loop here is that LuaJIT will bail out of this trace because it doesn't apply to the invariants that were encountered at runtime. or non-invariance. The invariant for which this code was compiled is broken. And it will take the fifth exit of this trace. And eventually it will compile a second trace starting from the fifth exit of trace 1, which is really just a single iteration of the loop where the index is even. And once it that is essentially nothing for the even index, it will return back to trace 1. However, one important thing to notice here is that in the current implementation of Luajit, it is unable to enter back into the loop body, which would be fair enough, well done. Instead, what happens in order to maintain a lot of the safety checks and invariance of the compiled program, it will instead jump back to the beginning of trace 1 and redo all the work that was hoisted out of the loop before entering the loop again. So we've seen that for branchy loops, the generated code that's generated by Luajit is not as ideal as the previous examples. Mainly this is because how it compiles the code. It will first compile a trace for the first type of iteration, first branch that it encounters while recording, and then compile a side trace, trace 2 here, for the other branches. And this is different from the behavior of an ahead-of-time compiler, because in the compiled code, these branches are speculatively biased by themselves. So whereas a ahead-of-time compiler would generate a branch within the loop while compiling the code ahead of time, what we have here is, in the case of Luajit, we have an extra code that's being jumped to if the branch is hit. Here. And specifically an implementation detail of Luajit means that the off branch will jump back to the head of the root branch, the root trace, and repeat this work, which would not have been repeated in an ahead-of-time compiler. And now I want to look at where this behavior really causes an issue. So in this example here, by a script generously supplied by Luke Gorry, we basically bring out one of the worst behaviors of Luajit. What we do here is we have a loop that we're going to run. We're going to run this program a bunch of times, and every time we run it, we're going to basically simulate some user input by initializing the random seed with the sequence of the outer iteration here. And in this program, we have a bias loop. This loop is biased based on the real world Russian roulette example. So in 1 out of 6 iterations, we will increment the die counter, and otherwise we're going to increment the live counter. And also what we're going to do is we're going to look at how this code was compiled by counting the instructions taken by the CPU to run this program in our perf log here. And from knowing how Luajit works, you can already see that how this is being compiled depends on the result of math random here in the iteration where the trace is recorded, the first trace. And as we've seen in the previous example, the second trace to be recorded will be biased in the code to have worse performance. So depending on whether our common case or uncommon case is speculatively biased by the compiler, we should get different results. And if I run this here, you get the expected outputs that yes, there's a 1 in a 6 chance to hit the die counter here. And if you look at the perf log, it will consist of something like that. So in this case, the first run of this program took 90 million instructions, meaning 90 instructions per iteration, because we're iterating for 1 million times here. And if we grab through that, just as like to get a rough overview, we'll see that about 80% of runs, about 80 of our 100 runs, we took around 70 million instructions, meaning 70 instructions per loop iteration. And on 20% of the runs, we took 90 million instructions. So in this case, the program was slower. And so what we see here is a case of bimodal performance, right? The simulated user input here had an effect on how the program was compiled. And in the good cases, if we're lucky, we get a compilation of the program that actually reflects the reality of the program, where this is much more likely to occur in this case, the biased branch. But in some cases, the compiler decides to speculatively prefer this branch and compiles worst case for the common case. So yeah, that's an issue. I consider this a bug in LuaJIT, and that's something that can be solved. There's papers on how this can be solved. It's just an implementation detail of LuaJIT that's at the present the way it is, and should serve to you as an example of the different issues and some of the downsides that you can hit in a JIT compiler right now. All right, so I hope I gave you a rough overview of what it means to do JIT compilation and how it can really help dynamic languages and dynamic language implementations. If I could interest you in this topic, I recommend you read the paper. It's much more detailed and goes into more ups and downs of just-in-time compilers, and also has some suggestions for alleviating some of the problems. Concluding, what I would like to conclude is that tracing just-in-time compilation is, in my view, a really powerful technique for implementing fast runtimes for dynamic languages such as Lisp. Also, trace compilation or JIT compilation in general is a very young and immature technology at this point. And there's lots of work to be done, and it would be amazing if I could motivate some compiler hackers to pick that work up. So yeah, at this point, I'm gonna thank you for your attention and hope I'm gonna see all of you next year in person at a offline ELS. And I assume there will be a chat room and I will be here for questions. Thank you very much.